The paper we're diving into today is Learning Latent Action World Models in the Wild.
This one comes from a team at FAIR at Meta in Nauria and NYU. The authors are Quentin Garrido, Tushar Nagarajan, Basil Terver, Nicholas Ballas, Jan LeCun, and Michael Rabbit.
All right, for everyone just tuning in for the quick summary, here are the key insights in about a minute. The big problem this paper tackles is a data gap.
A massive one. See, building a general world model, something that can predict the future, usually needs action labels. But almost all the video data out there, online in the wild footage, it's completely unlabeled.
So the solution here proves you can actually train these things called latent action world models, or LAMs, on just enormous, messy, uncurated video data sets. We're talking about things like YouTube temporal 1B.
And it works because the model is forced to figure out the actions on its own. It learns them.
And the really crucial insight, the thing that makes it all click, is how they design the action space. They found that continuous latent actions, the ones that are constrained to be either sparse or noisy, are just, well, essential.
Right. It's the only way to capture the sheer complexity of real-world actions. The old methods, like vector quantization, they just fall flat. They can't handle it.
And what's amazing is what these learned actions can do. They're spatially localized and camera relative. That means you can take an action, say, a person walking, and you can apply that exact motion to something totally different, like a flying ball in another video, and it just works. The ball starts walking.
Which leads to the final payoff, utility. You can train a really simple controller to map real robot actions into this learned latent space.
And suddenly, your world model, trained on random internet videos, can solve complex robotic manipulation and navigation tasks. And the performance is right up there with models that were trained on expensive, hand-labeled, domain-specific data.
It's a huge step. So, okay, let's really unpack this. We're going to get into how they managed to make these latent action models work on these massive, noisy data sets without any consistent agent or embodiment.
Okay, so before we jump into the LAM architecture itself, let's just quickly set the stage. The standard world model challenge.
Right.
A world model is basically a simulator for the future. You give it the current state of the world, let's call it to rest, and an action, at.
And it's supposed to predict the next state, rest plus one, that action, at. That's the key. It's the parameter that controls what happens next.
Exactly. And in a game or a sim, you have those actions. Move left, jump, grab. They're labeled.
But on YouTube, you just have pixels changing. The action is implicit. It's unknown. And that has always been the bottleneck for scaling these things up.
So the LAM framework tries to get around this by training two models together jointly. The first one is the inverse dynamics model, or IDM.
I like to think of this as the detective.
Yeah, that's a great way to put it. It looks at the before state, Urasanth, and the after state, rest plus one, and it has to infer the latent action that must have caused that change.
And then you have the second piece, the forward model. That's your simulator. It takes all the previous states and that inferred actions and tries to predict the future.
So the detective and the simulator are trained in this loop, right? They have to agree. If the IDM gets the action right, the forward model's prediction should be accurate.
Precisely. And that's where the difficulty just explodes when you move from curated lab data to in-the-wild video.
Because the action space is so much narrower in those old settings. A little robot arm movement, maybe a camera tilt.
But natural video is just chaos. I mean, it's richer, sure, you have people dancing, cars turning, complex finger movements on a guitar, but it's also full of noise.
You mean like leaves blowing in the wind, stuff that isn't a meaningful action?
Exactly. Leaves oscillating lighting changes. The model has to learn to separate a real causal action from just environmental jitter.
And maybe the most important part, there's no common embodiment.
Yeah.
It's not the same robot arm every time. It's not even always a person.
And that constraint is actually what forces the model to learn something really general. It can't just learn the camera moved left because half the time there's no moving camera. It has to learn a more abstract idea of motion.
Okay, so let's get into the architecture they use to handle all this complexity. The visual representations are key.
They are, and they made a smart choice here. They used a frozen VGP 2L encoder. Freezing it is important.
Why is that?
Because it means the encoder that's turning pixels into state representations isn't learning during this process. It provides a stable causal representation. You minimize the risk that the visual encoder itself is kind of cheating and leaking future information into the present state.
Got it. So the state representation is clean. And then the forward model, the simulator, is a big vision transformer, a VTL. How do they actually feed the action into that?
So they use something called an adapted Adelin zero mechanism. It's a way of conditioning the transformer frame by frame. It allows that latent action vector, ZOOT, to sort of modulate the internal layers of the VIT without totally disrupting its structure. It's a very clean way to inject the command into the prediction.
Okay, so you have this robust setup, and the latent actions themselves, they start as these 128-dimensional continuous vectors.
Yep. And it's all trained with teacher forcing on these short 16-frame clips running at a slow 4 frames per second. That slow speed is also deliberate to make sure there's a meaningful change between frames for the model to explain.
Which brings us right to the core problem, the thing they had to solve to make any of this work. How do you stop the model from cheating?
This is the absolute crux of it. Information regularization.
Right, because if you don't constrain that latent actions, the inverse dynamics model will just find the easiest possible solution.
Which is to compress the entire next frame, 6 plus 1, into the action vector.
Yeah, and then the prediction error is 0. But you've learned nothing about causation or action. You just learned a compression algorithm.
The action has to be the minimal explanation for the change, not the total explanation.
So they tested 3 ways to enforce this. The first one is sparsity.
The idea here is to make most of the elements in that 128D vector 0. So you're forcing it to be efficient. But just an L1 norm can cause the whole space to collapse.
So use something else, VCM regularization. Variance, covariance mean. It's inspired by VRReg.
And it's clever. It basically says, yes, be sparse, but also make sure the dimensions that you do use are carrying unique information, low covariance. So it stops the model from just packing redundant information into a few active slots.
Makes sense. The second approach is noise addition. This one sounds more like a VAE.
It is very VAE-like. You penalize the distribution of the latent action to force it to match a simple prior, like a standard Gaussian. By doing that, you're fundamentally limiting how much information it can carry. You're forcing it to be abstract.
And the third one they used as a baseline was discretization, just classic vector quantization.
Right, forcing the action into a fixed codebook. This has been pretty standard in older, more constrained world models.
So how did they stack up? The quantitative results on the one-step prediction error, that's really where the story is.
It is. This error is basically the performance ceiling. It's the best the forward model could ever do, given a perfect action from the idea.
And figure 4 in the paper just lays it out so clearly. The sparse and the noisy actions, they were flexible. You could tune them to have different information capacities.
But vector quantization, it just couldn't handle the complexity. It was stuck down near the deterministic baseline, the one with almost no information. The fixed code book just wasn't rich enough for the diversity of actions in that data.
You can see in the pictures, too, like the one of a person entering a room. The sparse and noisy models get it. They show the movement and they abstract the details.
But the discrete model's output is just this blurry, smeared mess. It's like it couldn't find a single word in its action vocabulary to describe that complex motion, so it just gave up.
Which really proves that for this kind of massive, wild data, you need these continuous, regularized, latent spaces.
For sure. And that finding really sets the table for the next part, the integrity checks. Okay, so the model can learn actions, but are they causal? Or is it still finding some clever way to cheat?
To figure this out, they came up with 2 really smart tests. The first one is the future leakage test.
This is all about making sure that Zayat, the action, doesn't secretly contain the whole next frame.
So what they did was they artificially created scene cuts. They take 2 different video clips and just swap the ends. So you get this completely nonsensical visual transition.
Right. And if the model was cheating, if Zeist already had the next frame baked in, then showing it a completely different random next frame shouldn't really matter that much to the prediction error.
But that is not what happened. The prediction error just skyrocketed. It more than doubled across the board.
We're talking like a 2.3 times increase for the sparse models, 2.5 times for noisy. That massive spike proves it. The dataset is just too complex for the model to memorize the next frame. It has to learn the transformation.
And you can see it visually, too. The reconstruction of the frame after the cut was this blurry, ghosted image. It had the general vibe, maybe the lighting, but none of the actual details.
Proving that the fine-grained visual info wasn't being leaked into the action, so test 1 passed.
The second test was for generalization. They called it action cycle consistency. This is a really cool one.
It's a great test for transferability, so it's a 4-step process.
First, you infer an action from video A.
Then you take that action and apply it to a totally different video, video B.
Then you re-infer the action from the result of that prediction on B.
And finally, you take that re-inferred action and apply it back to the original start of video A.
And the question is, how close is that final prediction on A to the one you would have gotten on the first step? If the action is truly general, it should be pretty close.
And it was. It passed with flying colors. On the kinetics dataset, the error only went up by a factor of about 1.13. That's a tiny increase after that whole round trip.
Which confirms the action space they learned is robust. It's reliable. You can transfer it across domains, and it still makes sense.
And this leads right to the heart of what these actions are. Because they trained on video with no consistent agent, the model was forced to learn something abstract.
It's not learning robot hand moves. It's learning generic camera-relative transformations.
That camera relative part is so important. The motion is defined from the perspective of the frame. You see it in figure 8. They take a locomotion action and apply it to a scene with two people.
And only the person who is closer to where the motion started in the frame actually moves. It's a localized relative command.
And the most stunning example of this is the cross-object transfer.
This is figure 7. It's amazing. They infer an action from a video of a man walking.
And then they apply that same latent action to a video of a flying ball.
And the ball just stops its old trajectory and starts walking. It moves left and a little forward, mimicking the abstract motion, even though a ball has nothing to do with a person.
So that lack of a common embodiment, which you'd think would be a weakness of the dataset, actually turns into its greatest strength. It forces this incredibly high level of generalization.
So now we get to the big question, the payoff. How useful is this universal action space for actual controlling things in the real world?
Right. Can we use this latent space as a kind of common interface for planning, whether it's for a robot arm or a navigation drone?
The method they use is pretty elegant. They just train a small, lightweight controller, a cross-attention adapter.
And its only job is to map a known, real action like a robot joint command, along with the history of what it's seen, into the correct latent actions.
That history part, using past representations, is super important, but it's a bit subtle. Why is it necessary?
Because the learned actions are camera relative. The controller needs context. It needs to know where the robot arm is right now in the camera's view before it can generate the right relative command to move it.
And if you don't give it that context,
it just defaults to outputting a latent action that means do nothing, which is actually a really sensible way to fail. It shows the context is critical.
Okay, so when they analyze the quality of the rollouts, basically simulating long sequences of actions on tasks like Droid for manipulation and recon for navigation, they found something really counterintuitive.
They did. I honestly had to read this part a couple of times.
You too. There was a clear lack of correlation between how well a model predicted the very next frame in the wild and how well it performed on these downstream planning tasks.
It's the classic Goldilocks problem. The models that were too constrained, they didn't have enough information in their actions to do complex tasks.
But the models that were too unconstrained, the ones that were best at one-step prediction, they actually did worse when you unrolled them over time. They seemed to be overfitting to short-term details.
Exactly. So the sweet spot, the best performance, was right in the middle ground of regularization. The action needs enough information, but not so much that it starts encoding noise or irrelevant future details.
The ultimate test, though, is the actual goal-based planning performance, using something like the cross-entropy method.
And here, these models trained only on random YouTube videos, remember? They achieved planning success on Droid and Recon that was right on par with, and sometimes even better than, baselines like Nomad.
And very close to models that were trained with explicit labeled actions. That result is a game changer. It challenges the whole assumption that you need that expensive labeling pipeline.
But here's the real paradox, the part we have to talk about, the noisy latent action models.
Yeah.
Which often had slightly worse raw prediction scores than the sparse models.
Ended up getting the best planning performance on the downstream tasks.
That is the single most important takeaway for anyone trying to build these systems. It means that raw prediction quality is not the same thing as utility for planning.
So what's the theory? Why would that be?
The thinking is that the noise constraint, by forcing the action space to be smooth and simple, like a Gaussian, might just create a space that's easier for an external planner, like CEM, to search through. It's a better search space, even if the individual predictions aren't quite as pixel perfect.
That makes a lot of sense. So finally, they looked at scaling, model size, data, training time.
And while making everything bigger generally helped the initial performance on the YouTube data.
The thing that gave the biggest and clearest boost to the final practical downstream planning performance was simply extending the training time.
That's a huge practical insight. If you have a fixed budget, this suggests you might get more bang for your buck by just training for longer, rather than immediately jumping to a bigger model or a bigger data set.
So, to sum it all up, this work pretty decisively proves you can train incredibly effective latent action world models just on massive, uncurated video. You could bypass the action labeling bottleneck.
And the key was moving to these continuous, constrained latent spaces, sparse or noisy. They can handle the complexity of the real world where discretization just fails. The result is this universal camera-relative action space that's general enough for all sorts of planning tasks.
So for you, the researcher or the ML engineer listening, what this really means is that our path to general agents might not require perfectly labeled domain-specific data.
Right. It might just require vast, diverse, unsupervised data as long as you engineer the model correctly to find those minimal causal explanations for what's happening.
Which leaves us with a final provocative thought to chew on.
Okay.
If this whole process of discovering latent actions works so well when you bolt it on after you've already trained a visual encoder, what happens if you integrate that learning loop directly into the foundation model pre-training itself?
Oh, that's an interesting idea. So you'd be jointly learning the visual representations and the action representations from day one in a single end-to-end process.
Exactly.
Yeah.
Imagine taking the IDM and forward model loop and baking it into the VGP2 pre-training. Could you create a new class of foundation model where the concept of action is just innate, not something you add on later?
That is a really exciting direction. It would be a much deeper form of causal understanding built right into the core of the model. I think that's definitely where things could be heading next.